I'm Phil Copeman, and today I'll be talking about understanding self-driving vehicle safety. As an overview, we're going to discuss what exactly do we mean by that word safety. And in particular, understanding safe enough for autonomous vehicles, but in a much broader context than positive risk balance. Is it safer than a human driver? Well, even if it is, there's a bunch more things you have to worry about, covering equity and negligence and recalls. And these are not theoretical considerations. These are practical situations we've seen play out and be a problem already with robotaxis. Then I'll talk about changing the scope of safety, going beyond net risk minimization and making safety look like a multi-constraint optimization. Now that may sound kind of abstract, but by the time we're done with the discussion, I hope it makes sense that we need a broader view of how we treat safety because there are no longer human operators to assume all those other responsibilities. The terminology affects how we think about safety, and while I'll be talking about robotaxis, I think this applies to things beyond autonomous ground vehicles. As a quick background, let's talk about machine learning and the V model. Traditional safety engineering loves to use the engineering V model. There's a concept of operations and requirements and detailed design on the left, and there's all sorts of testing on the right. And the idea here is that the first thing you do is you trace requirements to implementation. So you start going down the left-hand side of the V, doing verification to make sure each step as you go down the V corresponds to the previous step. By the time you get to implementation, you have reasonably good confidence the thing you're building is the thing the requirements we're talking about. You then do validation. Part of the validation is to see if there's gaps in the requirements, but a core part of the validation is making sure that what you built looks like what you thought you were building. Okay, so what about testing? How much testing do you do? Well, you don't test every possible thing because that's impossible. There's not enough time in the universe to test every possibility for a life-critical system. You just can't do it. It's not going to work. So what do you do instead? Well, what you do is the left-hand side of the V builds a prior expectation. You can think of it as a Bayesian prior expectation, if you want, of safety. And so you're pretty sure you're safe because you followed all the processes and you have good engineering design. So the validation isn't supposed to test everything. In fact, it's not really supposed to test safety. What it's supposed to do is to attempt to falsify the Bayesian prior belief that, you think you built something safe. Let's do some testing to make sure our engineering process did not miss steps, to make sure all the hazard mitigation we did really got mitigated, and so on. So the idea here is you need less engineering validation on the right-hand side, less testing, because you have a strong Bayesian prior belief that the thing you built was supposed to be safe. Okay, this is great. This is how safety standards work. Maybe not expressed the way you're used to hearing it, but this is the essence of why safety standards seem to work as well as they do. Now let's bring in machine learning. Well, we've got a problem, because we wiped out traceability from the left-hand side to the right-hand side. You do some concept of operations, you do some requirements in architecture down to some level, and then you turn machine learning loose on learning by example, and you get this thing out the end. But you have no idea why or if it implements all the stuff you asked it to do. You just know it does what it does. So you have this much bigger validation obligation because now you're testing to see if it's safe as opposed to testing to see if your Bayesian prior belief in safety is correct. Two completely different things, requires much more evidence. So you're going to need the extra testing. And you say, oh, that's no problem. We use a simulation. Well, all you've done is just kick the can down the road, and now you have to validate the simulator for all the edge cases. And how are you going to do that? Because the fundamental problem of life-critical safety in automobiles is hundreds of millions or billions of miles, depending on what you're talking about for fatalities. That's a lot of edge cases. And where'd you get the data in your simulator to make sure you covered all those things? So this is a fundamental, really hard thing. And we're going to call back to this as we do this discussion. So what should we mean by safe? Are loss events all that matter? Companies are talking about their injury rates and they're predicting they will have lower fatality rates. We don't have enough data to know yet how that will turn out. But there's more to safety than loss events. Here's an example. Here's a robotaxi entering a construction zone. Now those white signs are a little difficult to tell in this picture, but those white signs say road closed and you should not enter. And you can see there's a no right turn sign from the cross traffic and there's somebody holding a flag there in a colored vest, it's pretty obvious this road is closed to traffic for construction, but this robotaxi decided to go for it anyway. There was a lane open, presumably for construction crews to access the construction site. It said, yeah, it's fine. I'm going to go on in. Nobody was hurt, so this was never reported as a safety incident. Does that make it safe? Maybe there's more to safety than just counting up the amount of harm that's been done after the fact. How about the common idea that we should be, well, as good as a human driver is fine, which by the way includes all the drunk drivers. Is that okay? Well, no, it's not. It turns out there are a lot of things you have to do for safety, and we're going to go through each of these 7 things in turn to get a much more robust notion of what it is we actually mean by safety. Number 1, positive risk balance. This is the idea that the risk should be no worse for a computer driver than a human driver, safer than a human driver, or at least no worse. And typically when people talk about that, they're talking about fatalities and perhaps serious injuries. Okay, which human driver? 28% of crashes, and this is all US data, are alcohol, driving under the influence. 26% are speed-related. Those overlap. So the 9% distracted, the 2% drowsy, you don't add those up. They actually have overlaps among the crashes. But you're talking a good fraction, a good third to half of crashes have some of this stuff going on. And are you going to compare yourself to a drunk driver who's speeding and distracted and drowsy? Probably that's not what you want to set the bar, but some fraction of human drivers are like that. Also, a 60-year-old driver is 3.5 times better on fatality rates than a 16-year-old driver. It turns out that experience is better than quick reaction time. Experience matters more. Also, the where and who matters. In the US, there's about a 3.4 times fatality variation per mile traveled, depending which state you're in. And you go to specific zip codes, it's even more dramatic. There's huge variations depending on where you live. And the demographics of the victims change dramatically. Some states have a lot of pedestrian fatalities, some have fewer, some have more bicyclist fatalities, some have fewer, and so on. A lot of this has to do with infrastructure. They're the same drivers, but some roads are inherently safer than others. So which state are you in? If you're operating in a low-risk state and you claim you're as good as the national average, well, then you're probably worse than all the other drivers around you. And which vehicle? The average car in the United States is more than 12 years old at this point, and those 12 and 15 and 20-year-old cars do not have all the fancy active safety systems. They don't have the stability control. They don't have the automatic emergency braking, which any new car would, whether it's a robotaxi or not. So if you have a brand new car that happens to be a robotaxi, it's not really fair to compare it against the 20-year-old car that doesn't have any of the safety features, because that turns out that's where most of the safety is coming from. The automated steering is not giving you safety. It's the active safety features. When you're done, you have to ask which car, where, who, all these things to even get a credible baseline. And it's a really complicated problem. But we're not done. We're just getting started here. You also have to avoid risk transfer. What if children are at greater risk? Now, I'll give you a hypothetical, and I stress this is hypothetical to make the point. What if the number of fatalities, which is ballpark 40,000 per year in the U.S., what if it goes down to 20,000? Half the fatalities, and every single one is a child. That's not going to be okay. Now, to be clear, I did not say that would happen. I'm just giving you a thought experiment. If all the fatalities get concentrated in a vulnerable demographic group, that's not going to be okay. Now, if you just take a broad stroke and say, well, we cut it from 40,000 to 20,000, we saved half the lives. I'm not arguing that that's not a good thing. Saving lives is a good thing. But if the victims cluster on vulnerable demographics, that is not going to be socially acceptable even if you saved lives. There's more to it than just the net count. Now, here's a news story, and we have to be careful. This particular article's conclusion is controversial, so I'm not presenting this as factually accurate. There's some controversy here, but look at the headline. The headline amounts to this company knew it had trouble seeing children and it decided to operate anyway. Super bad headline. What if that were factually rigorous and it was a fatality count that children were more at risk to be killed? Again, there's no data to suggest that. This is a thought experiment. That's going to be a problem. And so when you say, well, that would never happen, well, how do you know it's not going to happen? It's a constraint on safety, and if you get it for free, great. But if you have to spend work on getting there, you're going to have to do that. You can't let this happen just by accident. So any increase in some group's risk, especially a vulnerable group, is going to be a problem for safety. You can't ignore that. So it's not only that you have to be safer on average, but you have to avoid risk transfer onto vulnerable populations, or you're not going to have a socially acceptable result. Number 3 is you need to avoid negligent driving. To be clear, I'm not a lawyer, but I've co-authored enough papers on this. I can give sort of a layperson idea of what's going on here. If you're a negligent driver, well, it starts with all drivers have a duty of care to other road users. When you get behind the wheel, you have a responsibility not to harm other people on the road to the degree you reasonably can avoid inflicting that harm. It's not okay to drive recklessly and put people in danger. You have a duty to not do that. That means negligence is a breach of that duty of care, and that causes a loss event. You have driven recklessly, and you've done something that a reasonable driver would not do, and has resulted in harm to somebody else. That's negligent driving in a nutshell. So can robotaxis drive negligently? Well, in the US right now, they do not actually have a duty of care to other road users, and that's a problem. Our legal system needs to address this. But the way I would look at it is, you ask the question, if a human driver had done the thing the robotaxi did, would they have been considered negligent? And if the answer is yes, we should consider the robotaxi negligent as well. There will not be public toleration of negligent driving that results in harm to road users just because it's a robotaxi. There's a tricky thing here about statistical safety arguments. If you say, well, we reduced fatalities from 40,000 down to 20,000, that's a net risk argument, and lower numbers are good. But negligence is a little bit different. If you're a human driver with the most amazing safety record there is, you do not get a free pass for running red lights. If you say, and a human driver is not going to be able to do this, I'm a human driver, I went 1 billion miles, I never had a traffic ticket, I never did anything wrong. Statistically, I would have killed 10 people by now. I've never killed anyone, but I decided I was in a hurry today, so I intentionally ran a red light and I killed a pedestrian. You should give me a free pass because I'm 10 times safer than the average human. People would just find that argument ridiculous. And yet, that's exactly the kind of argument that gets made for robotaxis, that we should overlook things that are a problem for them because they're busy saving lives. We're saving lives does not excuse negligence. Robotaxis need to be held to the same safety standards for negligence as human drivers. As an example, there was a 2023 cruise pedestrian dragging mishap. In this mishap, there were 2 things that were problematic with the behavior of the robotaxi. The first was that before any crash happened, the robotaxi accelerated toward a pedestrian in a crosswalk. Now, it turns out a human-driven vehicle next to the robotaxi also accelerated into a pedestrian in the crosswalk and hit the pedestrian first. But that does not excuse the robotaxi from an apparent violation of California road rules, and that acceleration put it in a bad position that it did not have enough time to stop when the pedestrian was thrown into its lane. A second problem with that incident is that after the robotaxi had hit the pedestrian and the pedestrian was under the vehicle, the robotaxi essentially forgot the pedestrian was there and decided to pull over to the side of the road, dragging the pedestrian along. It's pretty clear that a human driver would not have had that behavior. They would have known there was a pedestrian in the vehicle, and they would have done something other than deciding to start driving again. The issue here is, even if you were able to prove with rigorous statistical evidence that your robotaxis were 2 times or 10 times or 100 times safer than human drivers for fatalities, that is not going to get forgiveness for negligent driving behavior. Number 4 is standards set the expectation of safety. Remember I talked about that Bayesian prior belief on the V model? Well, one of the reasons we have a reasonable belief that our engineering efforts have established safety before we even do validation is we're following safety standards. And for robotaxis, there's a whole bunch of safety standards available. There's federal motor vehicle safety standards and the new car assessment program, which have to do with basic functions. They're not really about software safety. They're about whether the brakes work and the headlights are good and the airbags are good and things of this nature. But they're there. They're a foundation to build on. They don't prove you're safe, but they set a minimum standard for safety. There's cybersecurity standards. There are functional safety standards, which in simple terms make sure that either a computer-based function is working properly or it turns itself off so that something else can take over. There's dynamic driving function standards. This is about dealing with all the weird things that happen out in the world. Have you thought of everything? Have you covered it? Have you mitigated all the hazards? And there's system safety standards because drivers do more than drive. If you have a robotaxi, there's a lot of other safety considerations to think about. And that same system safety standard also covers how you assess whether your safety case really has everything you need in it. There are other standards cooking. They're coming out soon. Lots of standards. Trying to update this chart with all the safety standards has become hopeless. So this is just a quick introduction. The point is there are lots of safety standards issued. There are more on the way. The question is, are companies following them? Well, officially, if you ask companies to put in writing what they're doing, the only thing they're required to follow is FMVSS and NCAP because that's a U.S. government standard. All the rest of these standards are optional. Now, companies will say that they sort of follow it or they kind of follow it. Some of them say that more than others. Some of them follow some standards for hardware, but not for software. Most engineers will tell you if you get them in a private conversation, they're doing as much as they can for as many of these standards as they can, but that's not quite the same as independently assessed conformance. The car industry is unique in having a life-critical system with the kind of hazards present that is not required by somebody to follow their own standards, but that's where we are. Number 5 is fine-grained risk in regulators. Companies want to avoid regulatory recalls. There have been a huge number of software recalls, and we're up to the point where something like 1 in 5 recalls is software now, and that number is only going to get bigger. This means companies are going to have to spend more attention on trying to avoid software recalls. Now, what are recalls about? Well, recalls are about undue risk in the small. They're about specific issues, and they're informed by vehicle test-centric standards, but they can also be based on bad behaviors. As an example, we see NHTSA has recalls, Part 573 Safety Recall Report. By the way, just because the remedy is a software update does not make it other than a recall. A recall is the administrative process, which by definition has safety. It says so right in the title. It's a safety problem. Some recalls require a dealer visit. Some can be remedied via over-the-air update, but it's still a recall. It's still a safety defect that was out on the road in vehicles, sometimes for months or even years before the over-the-air update. So this is a real safety issue, but it's also bad press for the companies when they have to do a recall. The thing about recalls, though, is they're not for net risk. The recalls don't say, oh, your fatality rate is 20% higher than it should be, so you have to make some changes. It's not how recalls work. Recalls are for specific behaviors, such as rolling through stop signs or phantom braking or malfunctioning display consoles. None of those have a direct link to the net risk number in the recall. It's not recalled because it hurt the net risk. It's recalled because this is an avoidable bad behavior that can be fixed. So it's quite different than a net risk argument. And what we've seen is software quality and net risk are typically beyond regulatory scope. So you don't see a recall for bad software quality. You see a recall for the car does this dangerous thing, go fix it. Regulators are really struggling with software safety. There was a 2020 proposal to require the industry to follow all those safety standards I talked about on the previous slide, but that's inactive. Number 6 is ethical and equity concerns. Ride-hail made promises with disappointing results. The robotaxi companies are making very similar promises. I'll go over some of them in a moment. Is there any reason this should turn out differently? Robotaxi companies are in business to make money, and that's okay. But if they make promises and there's no mechanism to enforce or punish them if they don't do the promises, why should we believe they'll be any better at fulfilling promises than the ride-hail companies were? There are equity concerns. The taxi drivers were worried about being displaced by ride-hail drivers. That happened to a degree. Now ride-hail drivers are worried about being displaced by robotaxis. There's issues about disabled community access. The disabled community apparently was not well served by ride-hail, even though promises were made. But now they said because there's no human driver to discriminate against them, everything will be fine. I hope it turns out that way, but I'll note that as far as I know, there's no wheelchair-accessible robotaxi actually in service at this time. So far, it's just been promises. We'll see how that turns out. So the question is, do they actually deliver? Time will tell. Also, there's some societal issues. Cheap ride-hail really hurt congestion, and seems to have hurt public transit in cities. Even cheaper robotaxis can be expected to do that, but there's a safety problem associated with that. Public transit is dramatically safer than individual cars. So if an individual robotaxi is the same amount of risk as a human-driven ride-hail, and more people ride robotaxis, that's people moving from 10x, 20x safer public transit into much more dangerous taxis. You could easily see a net increase in fatality rates simply because of the mode change to more dangerous cars. There are also ethical and related concerns. It's common to hear people talk about, well, it's okay to have short-term safety problems because there'll be long-term safety benefit. But that safety benefit long-term is aspirational. We don't know if it's going to happen, but the short-term problems are real. There's also no required independent safety technical oversight. There is some permitting process, but the technical oversight is not particularly deep because the companies argue everything's proprietary and they can't share. In reality, the companies themselves are the only ones who have any way of knowing whether putting a new software release on the street will improve or reduce safety. And they're the only ones who know when it's time to pull a safety driver. They're making that decision without proper independent oversight. And that decision affects the safety of all the other road users. Number 7 is sustainable trust. The industry engages in trust-degrading rhetoric, such as robotaxis won't make stupid driving mistakes. The industry message is a relentless blame of human drivers. Here's a full-page ad from the New York Times, and it said humans are terrible drivers, and therefore, presumably, our robotaxis won't hurt anyone. But as I record this particular robotaxi is not able to operate on roads without safety drivers because it did hurt someone. There are trust-degrading actions such as lobbying for municipal preemption. The industry goes state by state and says that cities where the testing will take place do not have a say. In San Francisco, they cannot even write traffic tickets for robotaxis that break traffic laws. So the cities have their hands tied, and the states basically force the risk upon the local population. There's redacting withholding information. In the U.S., robotaxi companies are required to report crashes, as are companies with driving automation systems, but some of them are very heavily redacted, so no one actually knows what happened. The companies need to increase trust. I think they need more transparency on incidents and follow-up. They should accept proportional responsibility for losses. They should not say, well, it was less than half our fault, so that counts as zero. Instead, they should admit what role they played. Maybe it was mostly not their fault, a little bit their fault. Say, well, here's what we can do better. And even if they don't admit fault, they could at least say, here's what we plan to do to make sure the next crash does not happen. Typically, you don't get a lot of specifics. It's more like, oh yeah, we made a software patch, everything's perfect now until the next crash. And they should state and track their release criteria. How do they know that their next release is safe? And what metrics are they using to measure safety? We do get a little bit of after-the-fact net statistical results from some of the companies, but what we don't get is a fine-grained result of, yes, we made this change to fix this problem, and sure enough, our data shows it's fixed. We don't get the fine-grained outputs. Wrapping up this set of 7 points, the scope of acceptably safe for a safety case has to talk about many things. One of them is net statistical safety. Are you safer than an average driver? That baseline is very complex. It's a lot of work, but that's not the end. That's just table stakes. You then have to think about what your tolerance is for risk transfer. What's going to happen if your pedestrian risk goes up? How do you know you're going to avoid that? And so on. You have to think about what your tolerance is for negligent behavior. Robotaxis won't be perfect. Human drivers aren't perfect, but robotaxis need to behave in a way that is no worse than human drivers. And it may not just be at the net statistical level. It may be on a crash-by-crash basis to make sure that they're not driving in a negligent way, a way that a human driver would have been able to avoid. There needs to be a fine-grained absence of unreasonable risk. So you not only have to have net statistical safety, you also have to have an absence of avoidable dangerous behaviors that would lead to a recall. You also have to consider ethical behavior and equity concerns. It's not just a net statistical numbers game. Who gets hurt and how, and what other problems happen for society are also important for societal acceptance. Now let's expand the safety discussion to account for the things we've learned that safety is more than just net risk. Autonomous systems show us where to improve. One of the striking things about all the problems robotaxis have been having in California is that the vast majority of them have nothing to do with injuries and fatalities. There hasn't been a fatality. The vast majority of all the safety concerns have been other things that don't typically fall within the scope of a usual safety definition. So we'll do a definitional buildup starting with loss and ending up with acceptable safety. I'll have a slide on each one of these terms to give a proposed definition that is compatible with existing definitions, but broadens the scope to include concerns that we see popping up with robotaxis. There's a viewpoint that safety is too often thought of as an optimization problem. People say, well, the lower the net risk, the safer you are. And there's more to it than that. I think it needs to be a multi-constraint satisfaction problem. So you can optimize, but you have to meet all the constraints before you get to optimize. And nobody really talks about the constraints enough. So we'll reformulate safety in terms of first satisfying the constraints and then doing the optimization. Before we get into the definitions, it's reasonable to ask, so are the current definitions broken? Why do we need to do this? And the answer is, yeah, I think they're broken. And the problems only slowly became apparent to me as I was working through the definitions in the UL 4600 standard and as I was watching what was happening in California. So I'll give some examples to motivate why it's probably time to take a look at these definitions, but it's not just about the definitions, it's also about how we think about safety and the framework we need to use to justify safety of autonomous systems such as robotaxis. How about the definition of safety case? If you look at DefStan 00-56, it talks about a safety case, and it's a structured argument based on evidence and so on and so on. And at the end, it says, in a given operating environment. When I saw that, and I thought about it for self-driving cars, I said, that's a problem. Because we don't actually know what the environment is for these self-driving cars. We say we know it, but we're always surprised about things we didn't think about it. So a given operating environment implies you actually know what it is, but you don't because it's changing, it's incompletely specified. So when you encounter unexpected obstacles or unexpected vehicle types, is that in or out of the given operating environment? There's a risk here. The safety case amounts to saying, well, you're safe as long as we got our environment model right, but if there's a defect in the environment model, that doesn't count. Well, you may say it doesn't count for the safety case, but it doesn't stop the crash from happening. So there's a crash with a Waymo robotaxi that crashed into a utility pole. This one's kind of interesting. Utility poles, due to some sort of error in their system, were tagged as it's okay to hit utility poles. But curbs were not okay to hit. And this was not a problem because almost all telephone poles are behind curbs. So for an operating environment that is every telephone pole is behind a curb, everything's fine. But the first time they found a telephone pole to run into that was not behind a curb, they had a crash. Cruise had a crash in which they ran into the back of a bus, but this was a long 60-foot bus that had a joint in the middle, and they had only programmed and trained on buses that were 40 feet long. So even though the onboard sensors saw the back half of the bus, the planning logic decided to ignore the back half of the bus because it knew that buses were only 40 feet long and just drove right into it. In both cases, it's pretty easy to argue that the root cause here was problems with the model of the operating environment. And so they could have a safety case that might have proved they were absolutely perfect as long as their environment model was correct and their environment model was wrong. I will argue that limiting your safety case only to a given operating environment stops working when there's no human operator to take responsibility for policing the bounds of the operating environment. What about the definition of risk? Is the definition of risk broken? Well, typically it's a combination of probability and severity. See also positive risk balance, safer than a human. Okay, that has some appeal, but in practice, there are issues. What about risk redistribution onto vulnerable populations and all those things we talked about earlier? Here's an example of that happening. So this is not a hypothetical concern. In San Francisco, the fire department started collecting robotaxi incident reports because the companies were not required to report them. So the fire department collected their own and created their own database. And 11 out of 74 of their reports were in the Tenderloin district in San Francisco. This is an economically distressed area with high drug use. It's one of the most active emergency response areas in the United States, probably for those reasons. And they were seeing a disproportionate number of crashes in this pretty small area. If you look at some of the worst crashes that Cruise had a crash with a fire truck. The fire truck was responding to a fire with its lights on and its noisemakers on, and the Cruise vehicle failed to yield and got hit. and the pedestrian dragging mishap both happen right at the boundaries of the Tenderloin district. And to be clear, there's no fence or anything. These are pretty porous boundaries. But what you're seeing is arguably disproportionate risk imposed upon this vulnerable population, and maybe that's not okay. Maybe someone should think about that. So to address these, I think we need to expand the scope of what we mean by safety. To be clear, robots can fail even if they do not drive drunk. And they can fail in ways that are just software errors. We saw a couple of those, but they can also engage in what amounts to negligent driving. They may operate in ways that leads to uneven risk distribution, even though there's no line of code in it that's attempting to do that. And companies argue, well, that was rare, so it shouldn't count. But if you have a large number of rare things, in aggregate, they start piling up. Even though robots don't have the foibles of human drivers, nobody really knows if they're going to be safer or not at the fatality level, and for sure they will make plenty of mistakes. But there's no human operator to blame. You can't blame a human operator for negligent driving because it's just the computer. And so you ask, who's responsible for that? Who or what monitors for a given environment for the scope of the safety case? How do you get computers that are good at social interactions? Because driving is fundamentally a social interaction with all the other vehicles. So I think we need to broaden what safety means beyond what we've been used to doing to account for all the kind of things I've been talking about. So let's go down a set of definitions to get there. First definition of loss. ISO 26262 uses harm, which is physical injury to people. But what about other incidents? What about injury to pets? There are folks for whom their pets are extremely important to them. And just saying, well, we hit a cherished family pet, that counts to zero because it's not a person, is probably not the right answer if you want social acceptance. So I'm going to say that loss should be in any adverse outcome. And that includes not only harm to people, but anything, even negative societal externalities. We'll come back to those. Now, I'm not saying that all of them are weighted equally. What I'm saying is that they're all potential losses. You should consider all of them. And depending on your operational concept, the societal framework you're operating in, and so on, it's okay to weight them differently. But what you cannot do is say, well, the standard only says harm to people, so we can ignore the rest. We shouldn't do that. There are other standards which take a much more expansive view than 26262, and I'm going in that direction. And I'm using the word loss instead of harm to avoid confusion in the automotive industry, because loss has to be more than just physical injury to people. What about risk? Classical risk is some combination of probability and severity. For the automotive business, they also include controllability. By the way, how do you do controllability with the computer driver? Is the computer driver supposed to exert controllability? And so how do you know it's going to get that right and so on? That gets kind of problematic. But we also see recalls for patterns of losses. If you get a single loss event, you might blame it on driver error, whether it's human driver or computer driver. But if there's an aggregation of lots of loss events that all sound the same, then that also is something about risk, and it transcends the risk of the individual mishap. NHTSA recognizes this, and the typical NHTSA recall starts with a recitation of how many mishaps there have been. Most of the recalls are not actually about individual crashes. Most of the recalls are about patterns of losses they've seen in their data. As an example, there was one recall, which was 956 Tesla crashes with 29 fatalities. And what they found were some trends such as avoidable crashes, loss of yaw control, inadvertent auto-steer override. The auto-steer override is that a person who was twitching the steering wheel to convince the autopilot that the person was still paying attention would sometimes twitch it a little too hard and disengage the auto-steer without realizing it. And if it happens once, you can blame the human driver. But if you're seeing a very substantial crash rate due to that mistake, it's time to start blaming the driver interface instead of the individual drivers. So this is not just probability and severity. There's something about patterns of losses also matter. To that end, risk is going to include not only the probability, but also both individual losses and patterns of losses. And it isn't about the amount of the loss, it's about the importance to stakeholders. Because as we're seeing, there's some losses that matter a lot to society, even if a purely utilitarian view would assign them a low dollar value. Now let's talk about the definition of safety constraint. This is a new term you don't typically see in safety standards, but we need it as a building block to get to the endpoint. You have to ask the question, is your definition of safety just the net minimization of the sum of risks? Probably not. Here's the issue if you go down that path. what do you do about almost zero probability times nearly catastrophic consequence? What risk do you assign to that? Well, just ask the nuclear power industry how that's been turning out for them. And the issue is that things that aren't supposed to happen have a way of happening, and the catastrophic consequence can be objectively catastrophic and harm to people, but can also be dramatic reputational harm to the industry. In practice, this too often gets assigned as zero. And that's a problem because you say, oh, that's never going to happen. We'll spend zero on it. And when it does happen, it's an existential threat to the entire industry. So that's probably not the right answer. There's also risk due to negative externalities. How does a design team assign consequence to blocking a fire truck? You can say, well, we have a hazard. The hazard is we may have some sort of failure and it causes our robotaxi to stop somewhere. And in San Francisco, they had robotaxis blocking firehouse driveways because they decided to stop. And you say, it's no big deal. This is a fair response. It's justified. The team will come out in 10 or 15 minutes and get the car out of the way. Meanwhile, there's a fire alarm and the fire truck needs to go respond to the alarm and it's stuck in the firehouse because it cannot get out of the driveway. What's the consequence to that? Well, asking a design team who's doing a hazard and risk analysis to assign a consequence to blocking a fire truck is just unreasonable. How would they even know? That's not something you should be doing, but it's something that matters if you take out a human driver because there's no human driver there to get the car out of the way. So I would say, rather than saying that's within the normal realm of hazard and risk analysis for the car company, you should instead say that's a negative externality and you're not allowed to do it. What we have is rules and regulations. What I'm arguing is we can no longer say that compliance to road rules or compliance to regulations is not the problem of the safety standard, because without a human driver, the computer has to deal with this. As part of that, you also have reasonable road rule violations. Is it okay to cross the center line? Well, it depends, and somebody or something has to make a judgment call. So all these things are in scope for safety, but some of them are net risk minimization, and some of them there are a bunch of arbitrary rules imposed by the outside that you do not get to violate, and those are safety constraints. They're constraints on your safety case. You cannot argue, it'll probably be fine, we're not going to worry about that. No, the law is the law. You're supposed to follow it, barring reasonable exceptions. So a safety constraint is a limitation imposed on risk by stakeholder requirements, the things you're just not allowed to do even if you think it's okay. Now we do a definition of safety engineering. When we get to acceptable safety, you see why I need this as another building block. There's an expectation that testing alone does not create safe software. We've known this for decades. It's important to remember that no amount of road testing will prove that these systems are safe, especially since they get updated on a frequent basis. Nonetheless, the industry loves to tell us how many million miles or tens of millions of miles they have, and that must prove they're safe, keeping in mind they need at least an order of magnitude more to say anything about statistically significant fatality rates. But this is the messaging. And to counteract that, I think we need a definition of safety that emphasizes the way you get safety is not by brute force testing. The way you get safety is by doing safety engineering. So safety engineering is a methodical process, and I listed the things that you tend to find in safety engineering. If we want to have a discussion about what goes in the list and what comes out of the list, that's a great discussion to have. But I would argue if you're not doing hazard analysis, you're not doing safety engineering, or at least not in any form I recognize. Now we get to safety case. Now that we have safety constraint, safety engineering, now we can get to safety case. Remember I talked about given application in a given environment, how that was problematic. Who enforces the operational limits? In an aircraft, the pilot is supposed to not take off if the weather is adverse. But with a computer pilot, guess what? The computer has to enforce the operational limits, and you can't say, well, the computer knows fair weather and foul weather. I don't know who prevents that, right? It's got to be the computer. And what if the environment's unknowable in full? So that piece sort of has to come out of the definition of safety case once you have autonomous systems. And what about foreseeable misuse or abuse? There are numerous reports of drivers of automated vehicles that require an alert, attentive driver to ensure safety, deciding, oh yeah, I've been told that my car is safer than a human driver, so my plan is to buy a car and drive home drunk. To be clear, that's not my personal plan. I would never do that, but there are people who do this, and this is entirely foreseeable. In fact, it's pretty much guaranteed to happen with the current industry messaging. So saying that this is outside of the realm of a safety case is just denying something that we know is going to cause harm. That means we need a broader view of safety case. It has the usual words about structured argument and so on, but it's required to use safety engineering. You have to have safety engineering. You cannot just say, well, we did testing. And it has to meet a comprehensive set of safety constraints rather than just achieve net risk. Finally, we get to a definition of acceptable safety. The definition of acceptable safety is it's more than just positive risk balance. We've talked about these various things you have to deal with. And it has to meet stakeholder needs. If you ask a bunch of people what they mean by safety, they usually all mean different things. And all of those have to be considered. It does not mean you have to meet all of them in full. There's always a trade-off. But you cannot ignore stakeholders' considerations. So all these groups, the industry and the regulators and the road users, consumer advocates, all of them should get a say in what acceptable safety means. So this means acceptable safety is not optimized risk. Rather, acceptable safety is it meets all the safety constraints, one of which might be low enough net risk. But other constraints will be ethics and negligence and recallable behaviors and things like this. So in summary, I think we need a new set of definitions for safety because there's no human driver to handle surprises in the environment or enforcement of operational limits or do the right thing rule interpretation or legal and ethical constraints. A computer has to do those things or it's not autonomous. And our definitions for safety and the way we think about safety have to be updated to account for the envelope of things in safety just got bigger because now we're building replacement for human drivers as opposed to equipment for which the human driver takes ultimate responsibility. People can say, can't we just reinterpret existing terms? Let's not change the standards. Let's not change the terms. Let's just put out a white paper saying that you should think about safety in this bigger scope. Because the way we're talking about it doesn't break existing standards, it's just broader in scope. There are two problems here. The first is minimal compliance organizations are likely to fall short. A company that says we're only required to do what's in the standard and not a bit more is not going to pay attention to a white paper changing the terms to make them bigger. So the terminology needs to change in a way that's enforceable. And the second is that in a standard, the terms should say what they mean. It doesn't do anyone any good to have a standard with a bunch of words and then say, well, yeah, but that's not what they really mean. See this other thing? Our standards need to be updated to acknowledge the fact that safety just grew in scope. There's an extended paper that compares these terms to other safety standards that you can read. And with that, I'll go to a slide that talks about all the collected definitions we've been talking about: loss, risk, safety constraint, safety engineering, safety case, and acceptable. And finally, there's a slide with resources to follow up.